In this video, we're solving problem 14.8.026 from the Larson and Edwards Calculus Early Transcendental Functions textbook, 7th edition. We're asked to use a change of variables to find the volume of the solid region lying below the surface and above the plane region R. And we're given, this is our function, and the plane region R is the region bounded by the square with these vertices. Now, first of all, it's saying that we need to find the volume of this solid. So remember how we do volume. The volume of a solid between this surface and the region R is just the double integral over R of that function, provided that that function is positive over the region R. Okay, so this is the integral we want to evaluate, and this is the region. So first I would obviously state that double integral we're trying to evaluate. And then the next thing I would do is sketch the region R and try to come up with a suitable transformation based on my sketch. So I know that R is a square and it has vertices at these points. So it looks like the smallest x value here is pi over 2. So I'm going to make these increments, increments of pi over 2. That's pi over 2, pi, and then 3 pi over 2. Okay, and the region R is bounded by a square, and these are the vertices of the square. So when x equals pi, y equals 0. So that means that's 1 point on our boundary. And when x equals 3 pi over 2, y equals pi over 2. So that's here. When x equals pi, y equals pi. So that's that right there. And when x equals pi over 2, y equals pi over 2. Whoops. So that's our region R. It doesn't look very square, but if it was perfect, it would be a square. So that's what we're dealing with. Try to make it look more squarish. Here we go. All right. And so that's R. Now we'd like to think of a suitable transformation so that this integral will be easier to evaluate. I'm looking at this integrand and I'm thinking probably u equals x plus y and v equals x minus y, because that would make everything really simple. But I'm not 100% sure that's going to work. That would make my integrand simpler, but it may not make the region, the transformation of this region, simpler. So I think the best way to start is to take each of these boundary curves on R and find the appropriate equation for those curves. So this is x equals pi over 2, y equals pi over 2, and this is x equals pi, y equals pi. Okay, I think we can see those two the x and the y are the same there, and the x and the y are the same there. So that's a line that goes through the origin. We're going to have x equals y there. And this is x equals pi, y equals 0. And this is x equals 3 pi over 2, y equals pi over 2. I think those two lines have the same slope. They seem to be parallel, and we're told it was a square, so I bet they are parallel to each other. Let's find the appropriate equation of that line. Well, let's use rise over run. I go up pi over 2 and to the right pi over 2 to find this, to go from this point to this point. So pi over 2 over pi over 2, that's going to be a slope of 1. And the y-intercept is going to be some number down here. We could probably just find it by backing up twice. It looks like this is going to be y equals x minus pi. Now let's just be sure. When x equals pi, y is supposed to be 0, so I think that's going to work. If x equals pi, pi minus pi is 0. Okay, does that also work here? If x equals 3 pi over 2, 3 pi over 2 minus pi, is that pi over 2? Sure is. So those are the equations of those two lines. So we sketch the region R, and then we find the equations of the boundary curves. We've got y equals x, or x equals y, and y equals x minus pi. Good. Okay, and now let's find the equations of the other two boundaries. Those also seem to be parallel to each other. Okay, so on this one, we go down pi over 2 and to the right pi over 2. So I believe the slope there is going to be -1. Rise over run or fall over run. And then it looks like if that's our rise over run, if we go back over here, rise over run, fall over run, if we go back this way, it looks like the curve intersects the y-axis at pi. That's my guess. Let's check. When x equals pi over 2 here, y is negative pi over 2 plus pi, which is pi over 2, so that works. And then if x equals pi, do we get 0 for y? We do. Okay, so that's that one. Similarly, we go down pi over 2 to the right pi over 2. So the slope on that one is also -1. This one's a little bit harder to see. If we go backwards, what that would have to be. Let's just think about what the y-intercept would have to be. When x equals pi, y equals pi. So if this is pi and this is pi, I have negative, or y equals -x plus b, and at pi, we've got this. Add pi to both sides. Looks like b must be 2 pi. So we have y equals -x plus 2 pi. So those were two of the equations. And then here was the third, and then here's the fourth. Now this is just a conjecture. Let's make sure it actually works for these 2 points. When x equals pi, does y equal pi? It sure does. When x equals 3 pi over 2, does y equal pi over 2? It does. So we found the equations of the boundary curves. And now we want to take these and come up with a suitable transformation. We want to let u equal one function of x and y, and we want v to equal another function of x and y. And we also want to keep in mind this integrand. I've got an x plus y here and an x minus y here. I'm thinking to myself, is there any way I can manipulate these equations so that I would have an x minus y in them or an x plus y in them? I think we can see that, yeah, that would work. If I subtract y from both sides, this would give me x minus y equals 0. And if I subtract y from both sides here and add pi to both sides, I get x minus y equals pi. And here, if I add the x to both sides, I get an x plus y, which is what I want, because that expression x plus y is in my integrand. So this is x plus y equals pi. And adding x to both sides here, I have x plus y equals 2 pi. So that's pretty good. If I let u equal one of these guys and v equal the other one, that would give me a nice region. So let's say we found the equations of the boundary curves, and then we manipulated these to get expressions like this. And again, we were trying to manipulate the equation to get an x minus y because of that right there, or an x plus y because of that right there. And it turned out that that was pretty easy to do. And now if we choose the transformation u equals x plus y and v equals x minus y, then we'll have some bounds for our region S. So I'll say choose an appropriate transformation. Again, there are no real rules for this. It was pattern matching. It was me trying to come up with a simple way to describe this that would simplify our description of each of these lines, and at the same time, simplify our expression for the integrand. And when I saw that x plus y and the x minus y, I thought that's probably going to be the transformation. Okay, so we're going to let u equal x plus y and v equal x minus y. So this is v equals 0, v equals pi. And if u is x plus y, that's u equals pi and u equals 2 pi. So now we want to use all of that to sketch the region S. This is not to scale. U starts at pi and goes to 2 pi. V starts at 0 and goes to pi. It's v equals 0 here. Isn't that nice? Wouldn't you rather integrate over this little square than integrating over that square? I mean, this one's not too bad. You have to go from this line to this line and this line to this line. You have to do 2 integrals either way. And then you've got to integrate these expressions, which are kind of a pain, but this is nice. U and V both go from a constant to a constant. So let's see, what else do we want to do? Sketch S and state the bounds for U and V. So U goes from 0 to 2 pi, and V goes from 0 to pi. Okay, this is actually going to be pretty easy. Remember what we're doing. We're trying to find a volume, and the volume under this surface, it's a minus, excuse me. And the way we do that is we take this and we transform it into a new double integral. Rather than evaluating the double integral over R, we're going to evaluate this equivalent double integral over S. If this is our f of x, y, I want to write f in terms of u and v. So everywhere I see an x, I'm going to replace it with x of u and v. And everywhere I see a y, I want to replace it with y of u and v. And then I need to multiply by an area piece. And the area turns out to be the absolute value of the Jacobian times du dv or dv du. It doesn't really matter because it's a square. Okay, you can integrate with respect to whatever you want first. So we've got S and we've got a description of S. Good. Now we need a new integrand and a Jacobian, and we can substitute everything in and evaluate the integral. So let's do the new integrand next. f in terms of x and y was x plus y squared times sine squared of x minus y. And we chose u to be x plus y. And we chose v to be x minus y. So this ends up being u squared times sine squared of v. Not too bad. And now we need a Jacobian. Now the Jacobian is going to be a little bit harder this time. It's not difficult, there's just one extra step. Actually, I don't really need that vertical line yet. I'm going to take the absolute value when we're done. I'm going to make my thing prettier, my paper prettier. There we go. Here's, it looks a little better now, doesn't it? Okay. And the Jacobian is the determinant of this matrix. You take your first variable, differentiate it with respect to u and v. Take your second variable, differentiate it with respect to u and v. And of course those are partial derivatives. And then you evaluate this. Now, in order to do this, you need x as a function of u and v and y as a function of u and v. Unfortunately, we don't have that yet. All we have is this. But that's no problem. We can find x and y as functions of u and v by solving this system of equations. Okay. Now you might think that does not look like a system of equations at all. And you would be right. Oops. Because it looks like we just have a bunch of variables and there are no numbers here. But keep in mind what you want. You want x to be written in terms of u and v, and you want y to be written in terms of u and v. So you can think of this as a system of equations involving x and y, and you want to treat your u and your v like constants. Like if this was a 10 and that was a 5, how would you solve this? X and y are your variables. Those are the ones that you want to solve for. So it's actually not too bad at all. I'm solving this system of two equations and two unknowns. I'd like to get x by itself, and it's pretty easy to do that. Since we have a y here and a negative y here, if we add these two equations together, you get x or u plus v equals 2 times x, which implies that x equals 1/2 of the quantity u plus v, or 1/2 u plus 1/2 v. Okay, and similarly, start with the same system. Now you want to get rid of the x's this time and hang on to the y's. Well, in order to do that, I need the coefficients of the x to have opposite signs. So I think I'll multiply the second equation by -1 and then add these two guys together. So we'll have u minus v equals x minus x, which is 0, and y plus y is 2y. So y is 1/2 of the quantity u minus v, or 1/2 of u minus 1/2 of v. Easy breezy. The key with this is you have to remember what you're doing. Keep in mind that you're solving for x and y as functions of u and v. So when I see the system of equations, I think to myself, okay, treat u and v like constants. How do I solve this system of two equations and two unknowns for x and y? When I do that, it becomes pretty simple. And now that we've got these, it's pretty easy to find those partial derivatives that we need. The partial derivative of x with respect to u is 1/2. The derivative of that is 1/2. There's no u in that, so the derivative of that with respect to u, treating v as a constant, is 0. And the partial of x with respect to v is 1/2, using the similar reasoning. And over here, partial with respect to u is 1/2, and the partial derivative with respect to v is -1/2. Okay, so we've got everything that we need to substitute into the Jacobian. And let's see, what did we do? We solved the system of equations for x and y. And then we compute the first partial derivatives. Okay, 1/2, 1/2, 1/2, negative 1/2. All right. So I have 1/2, 1/2, 1/2, negative 1/2. Multiply across this diagonal, you get negative 1/4. Multiply across that diagonal, and you get positive 1/4, and you subtract. So we get negative 2/4, or negative 1/2. That's the Jacobian. You need the absolute value of that Jacobian right here. So we're gonna actually have absolute value of negative 1/2, which is a positive 1/2 right there. Okay, now that we've computed the Jacobian, we just substitute everything in. So the double integral over R of f of x, y is equal to the double integral over S. And in S, u went from 0 to 2 pi, and v went from 0 to pi. And we have u squared sine squared v here. That's our new integrand. And then we need the Jacobian, or the absolute value of the Jacobian, times dA. And since these are my bounds for u, I'll integrate with respect to u first, and then integrate with respect to v. Okay, the absolute value of negative 1/2, is positive 1/2. There we go. And remember how we do a double integral. Start on the inside and work your way out. So as far as we're concerned, sine squared is a constant. If it's sine squared v there, I can't pull that all the way out of the double integral because I still need to integrate it with respect to v. But I can pull it out of the u integral because it's constant with respect to u. Then I use the power rule for u squared. The antiderivative of u squared is u cubed over 3. We add 1 to the exponent and we divide by the new exponent and evaluate from u equals pi to u equals 2 pi. I will factor out that 1/3. 1/3 times 1/2 is 1/6. And then we'll have that upper limit cubed minus the lower limit cubed. Remember, whenever you've got a product and you're cubing it, you cube each factor separately. So this is 8 pi cubed minus pi cubed. That's 7 pi cubed times the integral from 0 to pi of sine squared v dv. Now this is an integral that cannot be evaluated using basic rules. It's not sine cubed over 3, although you'd be thinking in a very good direction. It does look like a u substitution, doesn't it? But the problem is there's no cosine out here. The integral of sine squared of v times cosine of v dv, I could do a u sub for that. With this, I can't do anything with it. So I would have to go back to my trigonometric integrals guidelines and see what they say. And they say that if the power of sine is even and non-negative, and so is the power of cosine, we want to use our power reducing formulas. So it turns out that sine squared of v is 1/2 of 1 minus cosine of twice the angle. The angle used to be v, now it's 2v. Okay, and you can pull that 1/2 out. 1/2 times that is just going to make that a 12 in the denominator. And then you look at what's left and you say, do I have a rule for that? And we do. So that's very nice. The antiderivative of 1 with respect to v is v. the antiderivative of cosine of 2v with respect to v is sine of exactly the same angle. And since there's a 2 inside, I've got to divide by 2. If I were taking the derivative, I would multiply by 2 by the chain rule. Since I'm taking the antiderivative, I divide by 2. And then we evaluate this from v equals 0 to v equals pi. And at v equals pi, this is pi minus 1/2 sine of 2 pi. Sine of 2 pi is 0. So I end up with just a pi here at v equals pi. And when v equals 0, this is 0 minus 1/2 sine of 0. Sine of 0 is 0, so it's just 0 minus 0, which is 0. In other words, when I evaluate at pi and 0, I get pi minus 0, which is just pi times this guy. So I end up with 7 pi to the 4th over 12. And if you're saying, what does that mean? Those are units cubed. That's the volume of this. You're saying, what's that? Well, that's a surface. It's given by this function. And we're looking at the volume between this surface and this region R in the xy plane. I don't actually know what that surface looks like. So here's my cartoon surface. There's z equals f of xy. And we're integrating over this little region, this little diamond-shaped region. So that's our region R, and we're finding the volume under this guy, above this guy. It's like the volume between that surface, the volume between that surface up here and that little diamond shape. And if you're saying, again, what is it? That's this. That's what we calculated right here. That's the volume.